Hi everyone, so welcome to this talk on the chaos engineering and serverless. You might have heard more and more now over the last couple of years about this thing called chaos engineering, especially from large tech companies like Netflix or Amazon, and how they talk about they kill their servers in production environments at random to simulate infrastructure failures that result in the loss of EC2 servers, just to see if the systems can still stay up when those infrastructure problems happen. It's certainly one way you can apply the principles of chaos engineering in practice, but chaos engineering itself is much broader. In the words of principlesofchaos.org, which is easily one of the best places you can go and read about chaos engineering if you want to get started, to understand its core principles. It defines chaos engineering as a discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. And it's becoming increasingly important to many organizations because we're building more capable but also more complex systems now, which have more complex and hard to predict failure modes. Not only that, the more moving parts we have, the more likely that we'll see a failure in one of those parts. And so failures can become more frequent in those complex systems as well. Which means more than ever, it's important that we do our best to safeguard the experience of our users even when those failures happen. And that's why resilience is such an important non-functional requirement nowadays for everyone. But what does it really mean to be resilient? Well, the definition for resilience is that it's the capability to recover quickly from difficulties or toughness. In other words, it's not about preventing failure, and that's important because in the words of Amazon's CTO Werner Vogel, everything fails all the time. And you have no control over when failures happen. All you can do is to prepare yourself for when they do happen, and they will. Eventually, everything will fail. Disk will get corrupted, CPU chips get burned out, people can trip over cables, and sometimes you also lose network capability because sharks like to bite those underwater cables, apparently. So yeah, us British people call it Sod's Law, but everyone else knows it as Murphy's Law, that anything can go wrong, will go wrong. And the goal of chaos engineering is to identify these weaknesses in our system where failures can happen before they actually happen and cause some system-wide aberrant behaviors. And we do that by using controlled experiments to learn about how our systems actually behave when failure conditions happen. In the same way that we write tests for our business logic, we need to test our system's robustness and the resilience against the turbulent conditions that it's going to face in production, which could be through organized events such as game days, where, for example, you gather together as a team and one of you would say turn off the networking on one of your servers and see how quickly your colleagues are able to identify the problem to see whether or not you have sufficient monitoring and diagnostic in place, or by maybe programmatically injecting failures into the system and see just how it handles them. So my name is Yan Cui. I'm one of the serverless heroes, and I've also been using Amazon to build production applications for over 10 years now, including the last couple of years working pretty much exclusively using serverless components, including migrating a social network to run entirely on serverless back in 2016. Nowadays, I spend half of my time working with Lumigo as a developer advocate, and the Lumigo is a troubleshooting platform for serverless applications that really make it a lot simpler for you to identify and troubleshoot those problems when they happen in production. Amongst other things, we can show you all of your transactions in terms of architectural component, alongside with all of your Lambda logs side by side so that you don't have to jump between different tools just to see a complete picture of what happened on a particular transaction. The other half of my time I spend working as an independent consultant, where I work with my own customers and I help them go faster for less by successfully adopting serverless technologies. And in my spare time, I've worked with Manning to publish a few books and video courses, and I've also self-published a couple of video courses myself, and I also host a weekly podcast called Real World Serverless, where I interview other builders who are using serverless in production. And several of my guests on the show have said the same thing about why they chose to go serverless. Ari Palou from Alma Media summarized this nicely, that using serverless helps you reduce the blast radius of failures, because even when they do happen, it happens with one execution or one container, and Amazon would replace the container right away for the next execution. And so you get much better resilience for your application, because the platform is now taking care of common infrastructure failures like servers or runtimes crashing, and you get built-in multi-AZ redundancy as well. And so when someone raises the question about, well, why are we then talking about chaos engineering for serverless? It's a legitimate question, but you've got to remember that failures happen at all levels. Even when you've dealt with infrastructure failures, you still have to think about application level failures, like missing error handling that allowed errors to cascade through the code chain and get all the way back to the end user, or failures in your processes whereby critical errors do not get alerted to the right people, and you have to rely on your customers to complain before you know something is wrong. And chaos engineering is not limited to just your application. I mean, sure, it can be used to test your infrastructure and your platform, but it can also be used to test the people and processes you have in your organization through things like game days, as we discussed earlier. And the great thing with building my application on top of managed services such as Lambda is that AWS is already doing all sorts of experiments to make sure that Lambda service itself and the infrastructure beneath your functions are highly resilient. So as a consumer, I don't have to worry about individual servers dying or other forms of hardware failures. But just as we have the shared responsibility model for the security of applications running in the cloud, just because Amazon is looking after the basic building blocks of our application, the underlying infrastructure, the hardware, the networking, to make sure that they are secure and reliable, I'm still responsible for my application code. And I can still use chaos experiments to identify weaknesses in my application and the practices and processes that I have in place. In terms of the tools available to me, you've probably heard about Netflix's Simian Army, where you have a bunch of monkeys for killing servers or injecting latency or killing an entire availability zone or even a whole region. And there are also commercial tools like Gremlin, where you can automate a lot of these experiments on your infrastructure. There are even open source tools that allow you to run Chaos Monkey logic through a Lambda function, so that you don't have to run servers just so that you can kill other servers. But what about our serverless architecture itself? I mean, we don't have access to the servers that are running our code, right? And so there are no servers that we can kill, but there are still lots of application level weaknesses and failure modes that can exist in our code. For example, maybe I have misconfigured my timeouts so that user-facing API functions can time out if the internal APIs they are calling have longer timeouts than it does. Or maybe I'm missing some error handling, which is incredibly basic mistake to make and also very, very common in practice. And in cases where a downstream system suffers an outage, maybe I'm missing a trick by not having some fallback strategy in place so that I can return some cached or default response even, so that I can mitigate a cascade failure here and try to degrade the user experience gracefully. So Gunnar, who is also a serverless hero, published a very useful and helpful library that allowed me to inject failure into a Lambda function so that I can run experiments against my application. And generally speaking, there are 4 different steps to any chaos experiment. Step 1, you have to know what normal looks like for your application. If everything is on fire all the time, then you don't have a steady state, and you need to get your house in order first and establish what normal working condition looks like. For example, my 99th percentile latency should be below 500 milliseconds, and there should be less than 10 HTTP errors per hour. That is my normal state. That's my steady state. And once you know what that steady state looks like, then you can start to hypothesize what would happen if something was to go wrong. For example, if one of the servers die, or what happens if DynamoDB starts acting up. And then you can inject failures to simulate those conditions that you want to test, but keep them realistic. It's really easy to get carried away once you start doing this. And finally, after you run the experiment, you go through the data to look for evidence to either prove or disprove the hypothesis by looking at metrics, logs, X-ray traces, or any other telemetry that you're collecting to look for evidence that your hypothesis about how your system would behave actually holds. So in terms of the capabilities we get from the Failure Lambda library that the Guna has published, we can inject the latency into our Lambda invocations. And as an experiment, what if we can use that? And as an experiment, we can use that to see what if a service that we depend on has an elevated latency. In this case, I have a very basic, very common setup whereby I have an API with API gateway and Lambda, and this Lambda function is gonna call another API, also API gateway and Lambda, and then to get some data back, a list of restaurants, so that you can then render some UI that displays the restaurants that a user can order food from. So seeing as we have some try catch here in case there's any error, and in this case if there's any error, we can return some default response. And our hypothesis is that if the second API was to take too long to respond, it's going to time out, and our try catch is going to handle this and return some default response because we have them wrapped inside a try catch here, right? What actually happened was, we got a 502 return all the way back to the caller. So instead of seeing a landing page, they got this instead. So what happened? Well, our function timed out after 6 seconds. So why is that? We can look at the logs. We can see that, okay, the last thing it was trying to do was to load restaurants from this particular endpoint. And what's happened here is that, the second function actually succeeded. It did return 200 eventually, but the first function still returned the 502 to the caller. And the reason for that is because the second function had a longer timeout than the first function. This is quite an easy mistake to make, especially when you have lots of Lambda functions calling other Lambda functions through API gateway and looking for in a request response fashion. And even when you get this right, there's also the potential misconfiguration between the maximum integration timeout that API gateway has to the maximum timeout a Lambda function have. So you could have a Lambda function that can run for up to 15 minutes, but API gateway would have timed out the request after 29 seconds. And then there's also cold starts, whereby potentially even if the second function had a shorter timeout than the first function, but by the time you factor into account the length of the cold start duration, then potentially the second function can still cause the first function to time out just because it had a really long cold start, because it's running, say, Java, and it's got lots of dependencies, so its cold starts can be measured in several seconds. So it turns out in this particular case, we have a mismatch of timeouts. Most of my functions have a default of 3 or 6 seconds timeout because that's just what SAM or the server framework defaults to. API Gateway itself has got a hard timeout of 29 seconds, but most HTTP client libraries are not designed for these kind of serverless environments, and they default to a timeout of 60 seconds. So our function timed out long before the HTTP request itself. And the simple fix here is to just align the timeout settings, right? But what timeout value would you use? I have seen two common strategies. Strategy 1, you divide the function's timeout equally across the HTTP requests you're making. So in this case, our function has a 6-second timeout, and it makes 3 HTTP requests. Each gets 2 seconds. But then some requests might get timed out even though it would have been fine if we just let it run, because there's more than enough time left in the invocation. And the second strategy is whereby we take a more optimistic view, and every request gets the full 6 seconds. But then our function ends up timing out even though none of the HTTP requests took too long, but collectively they took longer than the 6 seconds we had. Luckily for us, when it comes to Lambda, we can find out how much time is left in the current invocation using the context object. So a better strategy would be to set the HTTP timeout based on how much time is left in the invocation, but reserve some time at the end so you can do any recovery steps like logging the timeout events, publishing custom metrics, or fetch a cached response from somewhere. That way, every request is given the best chance to complete. But if they do end up taking too long, then we will time them out before they cause the invocation to timeout, which will end up with 502 and the cause of error to cascade. So if you look at this new version of the code, you can see that one of the first things I'm doing is working out how much time is left in the current invocation using the context object, and then minus the amount of time you want to reserve for recovery steps to work out what timeout I should use on this request. And then I'm going to make the same HTTP request as before, but using that timeout so that if it took too long, then the request is going to get timed out, but still leaving me with some time to perform recovery steps. In the case the request was successful, what we're going to do is we're going to take the result and we're going to cache it in this case, so that on another invocation where maybe the request took too long to come back, then we got a timeout exception. So in that case, we can check, well, do we have a previously cached response? If so, let's return that so that we return something rather than an error. And failing that, maybe what we could also do is we can ship the application with some default restaurants that we know are safe to return. And so in the case where we don't get any response back and we don't have any previously cached response, we can just return the default set of restaurants that we know are going to be open. The result of all this is a more resilient application, which is exactly what we want. And besides adding latency, we can also use the failure lambda library to cause a function to throw an exception to simulate what would happen if, say, the second function was to throw an unhandled exception and we have a 502 response instead. And for API functions, we can also force it to return a specific HTTP status code to make sure that we're handling different HTTP status code, not just the 2xx. And for function that uses the temp space, we can also simulate what will happen if we end up filling up the temp directory so that you run out of space. And as your function tries to write more data to the temp folder, it's going to get some IO exception. And we can also use the deny list to simulate what will happen if a function was to lose network connectivity to some service or some API somewhere. So we can use that to simulate what will happen to our app if, say, DynamoDB has an elevated error rate, or our Lambda function is not able to connect to DynamoDB because of some underlying networking issue. So in this case, again, very simple, very common setup where I have an API with API gateway, Lambda, and behind them, DynamoDB table. So in this case, I've got a function to fetch some restaurants from the DynamoDB table by doing a scan, which is probably not what you should be doing, but as a demo, this is fine. And the hypothesis is that, well, if something was to happen, then the AWS SDK has got built-in retries and everything will be fine because the retries with exponential backoff is going to fix the problem. And well, what actually happened was that the function timed out after 6 seconds. So somehow our hypothesis was disproved. As it turns out, the DynamoDB client for JavaScript defaults to a max of 10 retries with exponential backoff starting at 50 milliseconds. And the delay between each retry is calculated using this formula, which Mark Brooker, who is a senior principal engineer at the AWS, professor at the last, reinvented that this is his favorite formula of all time. And when you do the maths, the max delay between retries alone can easily push you over 6 seconds if you just get a couple of, say, throttle exceptions in a row. So it's no wonder that our function timed out. And the big question is, well, what can we do here to improve things? And this is not just a hypothetical situation that can happen. Many people have written blog posts that reports exactly this particular problem, whereby they see Lambda functions timing out, even though all the function is doing is just making one call to DynamoDB. So when DynamoDB is under stress, or when you are hitting your throughput limits against the provisioned table, then a function can end up retrying multiple times, and amongst all the different retries and exponential backoff, they took too long and the function ended up timing out instead. So what we could do here is override the default configuration and set a more reasonable max retry count for our function. And we can add a fallback as well. For reads, we can fall back to a previously cached response or some static default response. For writes, we can also queue up the write to a SQSQ or something so that it gets retried in the background. And for the JavaScript SDK, this is how you can set the max retries, so that in this case, we're going to retry failed DynamoDB operations 3 times instead of the default 10. And on a successful response, we are also going to cache the response so that in the future, if something was to go wrong, in this case, we can handle the exception by returning any previously cached response if one is available. Otherwise, we can return some default set of restaurants instead. And as we did previously, we can also apply a timeout against this operation based on how much time is left in the current invocation, so that if this operation was to take too long, we will time out the operation forcibly ourselves before it times out our function invocation. And again, the outcome here is that we end up with a more resilient system, which is exactly what we're looking for. So these are just some of the application failures that I can test to make sure that my application handles them correctly. But there's lots more you can do, including testing how your application handles spikes in traffic, or when you have different size of payloads, for example. Basically, anything that can possibly go wrong, you should be thinking about them and potentially testing them, because, as Werner said, everything fails all the time. So when you're thinking about resilience, don't stop at your application layer. Apply chaos engineering practices to your processes as well, and make sure that your procedures are both effective and that everybody is familiar with them, and everything is well drilled to make sure that when problems does happen, they can be identified and fixed quickly. And that brings me to the end of this talk. Thank you guys very much for being with us this afternoon. As I mentioned earlier, I spend most of my time as an independent consultant. So if you want to see how serverless can help you go faster or need some help upskilling your team, then let me know. Go to theburningmonk.com to see how we can work together. And once again, thank you everyone, and stay safe.